As an example, let's say that in a simulated experiment, we have 10 actions, and the ground truth expected reward mu A is chosen uniformly at random in the range between 0 and 1. And let's say that we run the experiment for 1 million rounds. And the green line here shows the theoretical worst case cumulative regret we get from the bound that we mentioned before. And the blue line here is the real cumulative regret we computed from running the simulated experiment. And we can see that these two curves actually have a very similar trend. Both are from the trend of log t. And another thing to know is that we can see that in practice is real cumulative regret is usually much lower than the theoretical worst case regret. So things are usually much better in the real world experiments. And next, let's talk about some use cases for the UCB or the epsilon gradient algorithm. So one use case is about news or ads recommendation. The problem setting here is that for new news and ads, we do not have enough signal about how good they are, right? And here, good means how likely are people to interact with them. And the idea is that we can actually think of each piece of news or ads as an M. And in this case, the user engagement, for example, click, can be considered as reward, right? And then in this case, we'll need to make the trade-off between exploration and exploitation. And by doing this, we will need to avoid keeping showing the best known news or ads and track the system into local optimal. And the solution of doing this is to use the bandit algorithms that we have discussed before. For example, we can use the UCB algorithm, or we can use the epsilon gradient algorithm. So usually in round T, this algorithm will observe a set of news or ads. So these are the arms that we can potentially pull. And in the second step of each round, then based on these payoffs from the previous trials, the algorithm will choose one arm from the set and will receive the payoffs R sub TA. So for example, in the UCB algorithm, we're going to choose the arm with the largest upper confidence bound. And note that only feedback from this chosen arm A is observed, and we don't know anything about what would have happened if we have chosen other arms. And the first step in each round is that the algorithm will improve the arm selection strategy with each observation. For example, we will update the expected revenue by using the new expected CTR times the bit amount we already know. And this part actually corresponds to the update of the average expected award, the mu A hat that we mentioned in the UCB algorithm. And basically, what this algorithm means is that if the overall score for a news or ad is too low, then the algorithm will just filter it out. Right? And another use case is about A/B testing. For those of you who are not familiar with A/B testing, A/B testing is actually just a control experiment with two variants, A and B. For example, let's say that we're trying to decide whether the variant A of the web interface is better or the variant B of the web interface is better. Then basically we will just randomly split the web traffic into two parts, and we'll assign some part of the traffic to variant 1 and we'll assign some part of the traffic to variant 2. And if it turns out that the click rate for the variant 1 is 52%, and the click rate for the second variant B is 72%, then we can say that variant B is actually better. Now imagine you have two versions of the website, and you'd like to test which one is better. And more concretely, let's say that version 1 has an engagement rate of 5%. So what does this engagement rate mean? For example, we can say that each session of a user is like 10 minutes, then the engagement rate is that the actual engagement time of this session from the user. So if it's 5%, then basically it says that 5% of the time the user is engaged in this interface or in this website. Now the version B has engagement rate of 4%. So in this case, the version B has a slightly lower engagement rate than version A. And the problem we want to solve is that you will want to establish with 95% confidence that version A is actually better. Now, if we do it naively by assigning the same amount of traffic to version A and version B, then you're going to need about 22K observations. So basically about 11K in each or in each version of this website. And note that how do we compute this number of 22K? We can just like use the t-test to establish the sample size we need to get this 95% confidence. So the question is, can Bandit algorithm do better than this? If we use Bandit algorithms, can we cut this number of observations we need, for example, by half or by 1/4? The answer, of course, is yes. So remember that if we use the naive solution by assigning the same amount of traffic to both variants, then we're going to need about 22K observations. And assuming that we have 100 observations per day, then in this case, we're going to need about 200 days to finish this experiment. So it actually takes a very long time. Then note that the goal of this A/B testing is just to find the best action, right? A versus B. And this is actually a very similar goal to our multi-arm Bandit algorithm, right? Basically, it's equivalent to the setting where we have only two arms, A and B, and we're trying to figure out which arm is the better one. Then by doing this, we can actually update this randomization distribution. So basically, how we distribute the traffic to version A and version B. We can update this randomization distribution as the experiment progresses. For example, one idea is that for twice per day, we can examine how each of the variants has performed, and we can adjust the fraction of traffic that each arm will receive going forward. For example, if we see that one of the arm appears to be doing very well, then we're going to give this arm more traffic. And in contrast, if the other arm is clearly underperforming, then we're going to assign less traffic to this arm. And basically, this means that this randomization distribution will be updated as the experiment progresses. For example, let's say that on the first date, we assigned about 50 sessions to each of the arms. So we assign 50 sessions to arm A, and we assign 50 sessions to arm B. And suppose the first arm A got really lucky on the first day, and it appears to have a 70% chance of being superior. Then we're gonna assign A with 70% of the traffic on the second day, and the other variant B will get the remaining 30%. Then at the end of the second day, we're going to accumulate all the traffic we have seen so far over both days, and we're going to recompute the probability that each arm is the best, and we're going to adjust the distribution strategy as the experiment goes. So let's say how this simulation actually turns out if we use the one of the Bandit algorithm. For example, if we use the UCB algorithm, it turns out that if we do this, and then the experiment actually can finish in only 66 days. So actually save you more than 100 days of testing, which is a lot. And another advantage of using this UCB or epsilon gradient algorithm is that they're actually very easy to generalize to multiple arms. So even if you have multiple variants of the website you want to test, you can still readily use this algorithm. We can see that it can actually still works very well.